Welcome back to Data Science series. It's day 8 of our 30-day journey to mastering NumPy. Today we were going to take a deeper dive into trigonometric, exponential and log functions in NumPy. These functions are essential for scientific and engineering applications, so understanding them is crucial. By the end of this video, you will have a solid grasp of these functions and how to use them effectively in your project. First, we need to import the NumPy library, which is essential for performing numerical operations in Python. So, import NumPy as np. Then run this. Next, we will create an array of angles in radians. We will use some common angles 0, pi by 6, pi by 4, pi by 3, and pi by 2. And here we use NumPy np.array to create a NumPy array and np.pi to represent the value of pi. Let's print these angles to see what we have. Now let's calculate the sine, cos and tan values for these angles using the NumPy trigonometric function called sine, cos and tan. The np.sine computes the sine of each angles, then the np.cos the cos functions, and np.tan the tangent. Okay, let's print this result to see the output. Next, we will find the inverse trigonometric function arcsine, arccosine, and arctangent. First, let's extract the sine, cos, tan values of the angles. Then we use np.arcsine, np.arccos, and np.arctan to compute the inverse function. np arcsine give us the angle for sine values. Then np arccos give us the angle for cos value. np.arctan give us the angle for tangent values. Let's print this result too. And that's it. We have used NumPy to calculate trigonometric function and their inverse functions. Let's dive into a problem. Suppose we have a right triangle with an angle of 30 degrees and a hypotenuse of 10 units. We want to find the length of the opposite and adjacent side. Let's use sine and cos to find this length. First, we need to import the NumPy library. This library helps us perform mathematical calculation easily. Import NumPy as np. In trigonometry, angles are usually measured in radians. We need to convert 45 degrees to radians. NumPy has a function for this, but since 45 degree is pi by 4 radians, we will use that directly. Angle equal to np.pi by 4. Next, we need to define the length of the hypotenuse, which is 10 units. Hypotenuse equal to 10. We can find the height, the side opposite the angle, using the sine function. The formula is height equal to hypotenuse multiplied by the angle, the sine of angle. Let's calculate this. And here np.sine of angle calculates the sine of the angle, and we multiply it by the hypotenuse to get the height. Next, we will create an array of values to which we will apply on exponential functions. Let's start by calculating the exponential function. This function is denoted as e power x, where e is a Euler's number approximately 2.71828. Here's the np.exp values calculate the e raised to the power of each values in the array. Next, we will calculate the exponential function with base 2. This function is denoted as 2 power x. Here, the np.exp2 of values calculates 2 raised to the power of each values in the array. Let's run this. Lastly, we will calculate the exponential function minus 1. This function is useful for numerical stability in some computations. Here, np.expm1 of values calculates e power x minus 1 for each value present in the array. Let's run this. Let's dive into a problem. Suppose we want to calculate the amount of money in a bank account after 5 years, given an initial amount of $1,000 and an annual interest rate of 5% component yearly. We can use the exponential function to solve this problem. First, let's import the NumPy library, import as NumPy. Let's say we have an initial amount of $1,000 in a bank account. The annual interest rate is 5% and we want to find out how much money we will have after 5 years, component yearly. First, I have created a variable named as initial amount equal to 1000. Then annual interest rate as interest underscore rate equal to 0.05, which is 5%. Then number of years the money is invested, which is years equal to 5. We can use the exponential function to calculate the final amount of money. The formula for compound interest is amount equal to initial amount multiplied by np.exponential of interest multiplied by year. Let's run this. Here the np.exp interest rate multiplied by year calculate the exponential growth factor and we multiply it by the initial amount to get the final amount. Now let's move on to log functions. Logs are the inverse of exponential functions and are used to solve equations involving exponentials. NumPy provides several log functions for different bases. First, import the NumPy as np. Then let's create an array of values on which we will apply log functions. Let's run this. Let's start by calculating the natural log of each values in the array. The natural log is the log to the base of e, Euler's number approximately 2.71828. Let's print this. Here, the np log values computes the natural log of each element present in the array. Next, let's calculate the log base 2 of each values. This function computes the log to the base 2. Let's run this. Here, np.log2 of values compute the log base 2 of each element present in the array. Now, let's calculate the log base 10 of each values. This function computes the log to the base 10. Let's run this. Here, np.log10 of values compute the log base 10 of each element present in the array. Lastly, let's calculate the log of 1 plus each values. This function is useful for accurately computing small differences. Let's run this. Here, np.log1p values computes log of 1 plus values for each element in the array. Let's dive into a problem. Suppose we want to find out how many times we need to double an investment to reach a certain amount. For example, if we want to know how many times we need to double 100 to get 1600, we can use the log base 2. Let's import the NumPy as np. Let's say we have an initial investment of $100 and we want to find out how many times we need to double this investment to reach $1600. So here initial underscore investment equal to 100 and final amount equal to 1600. Now we can use the log base 2 function to calculate the number of times we need to double the investment. The formula is number of doublings equal to log base 2 final amount divided by initial investment. Let's calculate it. Here np.log2 final amount by initial investment computes the log base 2 of the ratio of the final amount to the initial investment. giving us the number of doubling needed. That's it for today. These functions are foundational in data science and can be applied to various real-world problems. Trigonometric function for geometric calculation and spatial analysis. Exponential function for growth modeling in economics and biology. Log functions for scaling data, algorithm efficiency, and financial computations. Practice this example on your own, strengthen your understanding, and apply them creatively to solve problems in your field. If you have any question, drop them in a comment below. Don't forget to like, share, and subscribe. Hit the bell icon for more Python tutorials. Thanks for watching.